And here in this video, we're going to take a look at both tangential and centripetal acceleration. Now, from the previous videos, we should understand now that centripetal acceleration is caused by simply going around a circular path or even a curved path, and that the acceleration would always be perpendicular to the path, center seeking, inward to the center of the path's curvature. And of course, the magnitude is always going to be v squared over r. But then there could also be a situation where the object is both going around a circular path and either increasing or decreasing its speed. So here in this case, since the acceleration, we call that tangential acceleration, the acceleration in the same direction as the motion of the object. If that acceleration is increasing, meaning if the velocity is increasing, then of course there would be a different component or an additional component to the total acceleration. So let's also draw the centripetal acceleration, which would kind of look like this. So this would be a sub c. We could do the same over here, a sub c. Now you can see that in this case, the speed is actually decreasing, and so therefore we have acceleration in the opposite direction to the velocity. So we can see here that the object would be slowing down. Here we can see the object would be speeding up. But what would be the net acceleration? Well, the net acceleration would simply be the vector sum of these two. So in this case, the acceleration would be the sum of these two, like that. You can use the parallelogram method, and so this would be the total, the total acceleration of this object. And then here, in this case, you can see that if you add these two vectors up, then this would be the a total of this situation. Notice that in this case, the acceleration leads in the motion, the centripetal acceleration, and here you can see that a kind of lags the centripetal acceleration. But to find the magnitude, of course, of these two, the way you would do that is the magnitude of a total would be equal to the square root of the magnitude of the tangential acceleration squared plus the centripetal acceleration squared. So that's how we actually find the magnitude of that. But in this vector, in this video, I simply want you to understand what's going on. So let's see if you understand it. Let's have a situation like this where we have a skier coming down a hill. And then the hill bottoms out and starts going up again like that. So here's a skier. Let me see if I can draw a skier. I'm not that good at drawing, but here we go. Here's holding the ski poles. There we go. Coming down the hill. So what do the accelerations look like at various points along this path? Well, in this case, there would not be any centripetal acceleration because the path is straight. So there only would be tangential acceleration. So there would only be acceleration in this direction, which also would be therefore the total acceleration in this case. So you can say that would be the same as the total acceleration. So that would be a total, nothing there, nothing changes there. All right, now what happens at this stage right here where the path begins to curve? Well, at this point, since there's a slight curvature here, the skier would feel a certain amount of centripetal acceleration, not very large, small amount of centripetal acceleration. And because the path is not quite as steep anymore, the tangential acceleration would be a little bit smaller along the path direction like this. So this right here. So the tangential acceleration would be a little bit smaller. And you can see that the total acceleration would look kind of like this. That would be a total. Now, a little bit further down the line, you can see that the curvature is a lot steeper, so the centripetal acceleration would get to be a lot larger. Since it still slopes somewhat downward, the skier is still accelerating, so you'd still see a small tangential acceleration like this, a tangential, and of course the total acceleration would look like this. That would be a total. All right. What would happen if then the skier gets to the very bottom? At that point, the skier would not be gaining any more speed. So the only acceleration the skier would experience would be centripetal acceleration. And at that point, that would probably be a larger component because that would be the steepest part of the curvature. I should say the steepest part, but the greatest curvature. So that would be a sub c right there. A sub c. This is a sub c right there. And of course, there would not be any tangential components. A little bit further along the line, you can see that it's not quite as curved anymore, so the centripetal acceleration would become smaller, acentripetal, and of course at that point, since the skier is going uphill, there would be a negative acceleration opposite to the direction of motion, like so. So it would be the tangential acceleration. And of course, then the combined total acceleration would be the vector sum of those two, like so. And so that would be A total, the total acceleration. So here you can see that as the skier is slowing down, the total acceleration is ahead of the centripetal acceleration, and here it falls behind the motion because then the skier is slowing down. So that hopefully helps you understand how the tangential and the centripetal acceleration interplay to give you total acceleration on various components or various positions of that motion on that curved path. And that's how we look at tangential and centripetal acceleration. And in the future, some future examples, I will calculate the actual amount of these accelerations. So stay tuned if you're interested to see how that's done.